Good afternoon. Today we are hosting a webinar to discuss an NTSB safety report that will be released shortly. The title of the safety report is Commercial Vehicle Onboard Video Systems. The organizers and presenters of the webinar are myself, Kristen Poland, and Thomas Barth. We are both investigators at the NTSB. For this webinar, please note that your phone is automatically muted with this system. You will only be able to hear Tom and me, and we won't be able to hear you. If you have a question, either about the webinar or about the content, please type your question in the question box under the webinar screen. At the end, we will try to answer as many questions as possible. The National Transportation Safety Board has investigated many highway crashes where onboard video systems recorded critical crash-related information. During this webinar, we will give you an overview of the two main types of onboard video systems. Then, we will briefly review some of the NTSB's history using video systems in its crash investigations. Next, we will discuss two recent crashes where continuous video systems were installed on commercial vehicles. The first example was on a school bus in Port St. Lucie, Florida, and the second was on a motor coach in Kearney, Nebraska. Further, we will discuss the benefits of these onboard video systems and some limitations encountered during our crash investigations. Finally, we'll summarize the conclusions and recommendations that will be issued in this report. The NTSB will not be holding a public board meeting for this safety report. The purpose of this webinar is to provide you information about the report prior to its public release. We plan to release the report tomorrow morning. In addition, the webinar is being recorded for future use. The two types of onboard video systems, continuous and event-based, have distinct features. Continuous video systems start recording when the vehicle ignition is turned on and typically record for a program period ranging from 1 to 60 minutes after the ignition is turned off. These systems may capture video data surrounding an event, such as a crash, but because they record continuously, they also capture data that a triggered system may not record. Currently available continuous video systems advertise frame rates from 10 to 60 frames per second, depending on the number of cameras. Event-based video systems capture and save recorded data when an event, such as a crash or hard braking, triggers the system. A recording period usually captures 15 to 30 seconds prior to the event and ends 30 to 60 seconds after the event. Less than 2 minutes of data is typically recorded for each triggered event. The video frame rate varies depending on the storage capability of the system and the video settings. Today, event-based systems are often used in conjunction with driver feedback programs to increase safe operations. The event trigger is usually based on a measured vehicle acceleration with a set point above the normal operating environment. The safety benefits of onboard video systems can be summarized in three main categories. First, these systems provide identification and remediation of risky driving behaviors, such as distracted driving and drowsiness. Second, the systems also enhance the monitoring of passenger behavior, especially to address bullying, theft, and security. And third, the systems enable an enhanced collision review and analysis. Some of these benefits are suited to the continuous recording systems, while others are suited to the event-based video systems. The NTSB has encountered both continuous and event-based systems in our crash investigations. The next slides provide a brief overview of the NTSB's history using onboard video systems during its crash investigations. The first case we will discuss occurred in Conasauga, Tennessee, and the second occurred near Mexican Hat, Utah. The crash dates and the NTSB numbers are listed for your future reference. In the Conasauga, Tennessee crash, a continuous video system provided critical data in the investigation of a crash where a school bus was struck by a freight train. School bus drivers are required to stop, look, and listen at all passive grade crossings. As you can see from this crash animation, the school bus did not stop at the grade crossing. The 1999 school bus was equipped with one of the first continuous video systems available. The onboard video showed that the school bus driver had disregarded safety procedures and crossed the tracks without stopping on the day of the crash and on at least 8 previous occasions. One aspect of the resulting NTSB recommendations to the states was to periodically review onboard videotapes, especially with regard to driver performance at grade crossings. In the second crash near Mexican Hat, Utah, a motor coach equipped with a DriveCam 2 event-based video system ran off the road and overturned. The recorded data allowed the NTSB to determine the speed of the motor coach, provided information that the bus headlights were not on. The bus headlights were on at the time of the evening crash, verified that the driver was not using a cell phone, and documented both driver and passenger actions, such as evidence of fatigue. As many of you know, the NTSB is prohibited from releasing video showing vehicle operators or any occupants. Forward-facing video can be released if the operator or other involved people are not visible. The video recorded in the Mexican Hat crash included a forward-facing view, which I will show here. In this forward-facing video from the Mexican Hat bus, the vehicle dynamics can be evaluated. The video is shown twice. Although the DriveCam 2 system recorded only 20 seconds surrounding the crash event, the recorded data were critical to the investigation. Recently, the NTSB investigated 2 crashes where continuous video systems were installed on commercial vehicles. The Port St. Lucie, Florida crash occurred about 3:45 in the afternoon when a Peterbilt truck-tractor semi-trailer struck a left-turning school bus, resulting in a severe lateral impact collision. The school bus was occupied by the driver and 30 elementary school students, and was also equipped with lap belts at all passenger seating positions. The truck-tractor, in combination with a flatbed semi-trailer, was loaded with sod and occupied by the driver only. The school bus driver had entered a left turn-only lane. The bus driver then turned in front of the eastbound truck, which collided with the right side of the bus in the vicinity of the rear axle. Following the impact, the school bus spun clockwise approximately 180 degrees and came to rest facing back the way it had come. The truck departed the roadway onto the grassy right-of-way along the southeast side of the intersection and rolled to the left, coming to rest on its left side with the trailer resting upside down. In this picture, you can see the final rest positions of the school bus and of the overturned tractor-trailer that was carrying sod. The Port St. Lucie school bus was equipped with a continuous video and audio system. The system, manufactured by Seon Design Incorporated, had 4 interior-mounted cameras. All cameras were directed toward the inside of the school bus. In addition to the passenger compartment and front loading door, a portion of the driver was visible. The video system recorded at a rate of 15 frames per second, and a total of 55 minutes, 39 seconds was recorded. The videos began prior to the loading of the school children and continued through the bus trip to the point of the collision and after. The 15 minutes of video recorded post-impact included vehicle motion, occupant motion including belt position, and post-crash events capturing short-term injury outcomes, passenger egress, and the initial response of passers-by and emergency medical personnel. The second crash occurred in 2011 in Kearney, Nebraska. The crash began about 2 a.m. and involved an overturned tractor-trailer blocking westbound traffic. The overturned truck was impacted by another tractor semi-trailer and a motor coach. As a result of the collision, the motor coach had extensive front-end intrusion and deformation damage, which you can see in the upper right corner of the slide. The motor coach was occupied by the driver and 35 passengers and was also equipped with lap shoulder belts at all passenger seating positions. This slide further explains the three-event crash. The driver of the Volvo truck trailer drifted off the roadway into the median, shown with the yellow arrow, attempted to re-enter the westbound travel lanes, overcorrected, and the vehicle rolled 90 degrees onto its left side and came to rest across both westbound lanes of the interstate, with the underside oriented toward oncoming traffic. A short time later, a Kenworth truck trailer, shown with the white arrow, and a 2012 motor coach, shown with the orange arrow, came upon the overturned Volvo truck tractor. The Kenworth truck was able to move off to the right shoulder, just sideswiping the Volvo's front bumper. After braking, the motor coach collided with the overturned Volvo semi-trailer between the rear frame and the landing gear, separating it into two sections, and came to rest in the median. The 2012 motor coach was equipped with a continuous audio and video system manufactured by Safety Vision. The system had 4 active cameras, including a forward-looking camera, showing the view in front of the motor coach. The system recorded audio and video for a total of 30 minutes and 44 seconds. The recordings began prior to the bus departure and continued through the bus trip to a point immediately prior to the collision. Due to impact damage, data were not recorded during or after the crash. At this point, Tom will describe some of the specific benefits and limitations of the video system data from the Port St. Lucie and the Kearney investigations. Again, the crash dates and the NTSB numbers are listed for your reference. Tom?
Hello and good afternoon, everyone. The continuous video system on the Port St. Lucie school bus provided data to confirm that the driver was not distracted by a cell phone or other portable electronic device, and that he had both hands on the steering wheel during the left turn maneuver just prior to the collision. In addition, it was apparent that the driver perceived the impact threat, though too late, because he turned his head towards the oncoming truck. The onboard videos and associated audio recordings showed that the driver encouraged seatbelt use at the beginning of the trip and that he did not appear to be distracted by the students just prior to the collision. The video recording system also yielded information on passenger behavior. The continuous recordings documented student loading onto the bus and the use of seatbelts for most students. Although some views were partially obscured, including the seating position of the fatally injured student. The video also showed occupant positions throughout the bus trip. These data helped investigators establish an accurate seating chart, pre-impact positions, and the level of restraint for most of the passengers. Pre-crash video and audio documentation showed that the driver's attentiveness to passenger safety and seatbelt rules was a factor in the number of students who wore and properly adjusted their seatbelts. The most beneficial data obtained from the Port St. Lucie onboard video system were related to the crash sequence and post-crash environment. The 4 interior cameras remained in place and functional throughout the crash event and continued recording for more than 15 minutes after the initial impact. Although the school bus was not equipped with a forward-facing camera, the videos provided valuable information concerning the vehicle dynamics both prior to and during the crash, allowing investigators to calculate speed and position of the school bus prior to and after the collision. For the first time ever, belted occupant motion was documented on a school bus throughout the entire crash event for each occupant who was visible on one or more of the interior videos. Because of the extensive amount of motion captured, the NTSB worked with a team of outside experts to document the content of these videos and to ensure that the data were both accessible and useful to the research community. The factual reports in the NTSB docket for this accident document unique information on pre-impact occupant positions, occupant to vehicle and occupant-to-occupant impacts during the crash, flailing characteristics and ranges, rebound severities, and occupant final rest positions. During the period after the bus came to final rest, the video system documented evacuation, passenger loss of consciousness, passengers regaining consciousness, and emergency response. NTSB investigators were able to compare detailed information about the passenger injuries and the responses of the passengers during the post-crash period recorded on the video system. One limitation of this system resulted due to the positioning of the cameras. Neither the kinematics nor the final rest position of the fatally injured passenger, who was seated in the second-to-last row of the bus, was visible during the crash event or when the bus came to final rest. We were able to obtain limited information about this passenger from observations of other bus occupants and the responding passersby. In the case of the Kearney crash, the motor coach driver was not visible to any of the cameras. Her actions could still be inferred from the vehicle motion captured in the forward-facing camera. Images captured by the 3 other cameras, though intended to show the passengers inside the bus, were of extremely limited value. All 3 cameras were poorly aligned or rotated sideways such that only a very small portion of the passenger space was visible. Moreover, because the bus lights were off and the video system lacked the capability to see in low light conditions, the recording provided no pre-crash occupant position or restraint use information for the passengers. The forward-facing camera on the Kearney motor coach provided critical pre-crash information on the relative positions of the involved vehicles and some information about the sequence of events. The video showed roadway scrape marks from the first event when the Volvo truck overturned, the lighting conditions of the overturned truck as seen from the approaching motor coach, the initial position of the motor coach behind the Kenworth truck, the motor coach's movement into the left lane to pass the Kenworth truck, and the Kenworth truck's initial motion towards the right shoulder. However, this continuous video system was limited. The camera did not record vehicle dynamics data during the crash or the motion to final rest because the system was partially damaged as a result of the collision. Additionally, occupant motion during the crash sequence could not be evaluated because of the lack of low light capability, and the recording ended prior to the collision. In summary, this report found multiple benefits of onboard video recording systems for crash investigation. The use of continuous and event-based systems can provide valuable information for evaluating the circumstances leading to a crash, as well as critical dynamic information essential for assessing crash survivability. In addition, the systems can show occupant motion, restraint use, and injury information, which is unique and extremely valuable to understanding the circumstances of a crash and to better protect occupants in future crashes. Further, these onboard video systems, along with the driver feedback program, may provide a long-term safety benefit for equipped vehicles. The research is showing these trends. The NTSB is interested to see if equipped vehicles may actually be safer in the long run. The report also highlights onboard video system benefits that are not related to crash investigations. For example, video systems can be used to monitor passenger behavior and dissuade negative actions, such as bullying or theft, to monitor traffic surrounding the vehicle and assist in recording the observance of traffic laws, and finally, to enhance driver safety through feedback programs that correct potentially unsafe behaviors. The report also identifies several limitations of these onboard video systems. For example, although the continuous video system in the Port St. Lucie school bus documented critical post-crash information regarding evacuation and loss of consciousness, it provided inadequate visibility of all passenger seating positions. As a result, the fatally injured occupant was not visible during the crash sequence, and information concerning his motion, impacts, and potential injury causation were extremely limited. Having visibility of all occupant seating locations is critical for cases such as this one, but also for situations such as bullying or theft. In addition, improper camera positions and the lack of low-light recording capabilities on the Kearney motor coach caused inadequate data capture of occupant pre-crash position and restraint usage. Obviously, if the cameras are not positioned to show the passengers, the cameras cannot record useful information to address security or safety. Furthermore, the bus often operated overnight when the interior lights were turned off. Without low-light capability, all interior videos at night are unusable. And finally, video frame rates were low for both systems, which limits the ability to evaluate dynamic events. The NTSB is aware that onboard video systems are being installed for a variety of reasons. Recommendations detailed in this report are issued to encourage you to consider certain aspects of video system installation that would help us and you to achieve your real goals. The NTSB will issue 3 new safety recommendations in this report. The first recommends that the National Highway Traffic Safety Administration incorporate into their existing crash database systems, with appropriate access controls, standardized procedures for collecting and using pertinent video recordings, injury information, and crash data from video-equipped buses, consistent with privacy regulations and policies. The second recommendation is issued to multiple associations, including the American Bus Association, United Motor Coach Association, American Trucking Associations, American Public Transportation Association, National Association for Pupil Transportation, National Association of State Directors of Pupil Transportation Services, and National Transportation Association. It recommends the groups to encourage their members to ensure that any onboard video system in their vehicles provides visibility of the driver and each occupant seating location, visibility forward of the vehicle, an optimized frame rate, and low light recording capability. The final recommendation is to the manufacturers of onboard video systems and recommends that the manufacturers develop written guidance for the initial installation and long-term maintenance of onboard video systems and publish that guidance on their websites and in future owner's manuals. This recommendation is specifically made to avoid unusable camera positions and orientations as seen in the Kearney accident. As part of this report, the NTSB will also issue a safety alert addressing tips for improving the utility of onboard videos. The graphic on this slide shows a small portion of this safety alert that will be released in conjunction with the safety report. In addition, staff developed an article summarizing the main issues of this safety report for use by the associations receiving the report recommendations. A short excerpt of the article is shown in this slide. The article will also be available when the report is released. The NTSB dockets for the Port St. Lucie and Kearney crashes, as well as the historical crashes discussed, are open and available on the NTSB website. The yellow circle in the slide indicates the docket link on the NTSB homepage. Tomorrow morning, we will issue a press release with links to the report and safety alert. In addition, letters to the recommendation recipients will be sent tomorrow. Thank you for attending the webinar. This concludes the planned presentation. We will now take questions. Please remember to type your question in the question box under the webinar screen.
Thanks, Tom. It looks like we do have several questions. So the first question is, how can we get a copy of the webinar? And so the answer to that question is that I will send an email to all of the attendees with information on how to access the recording of the webinar. And that may take a couple days for us to process that video information and to make it publicly available for all of the attendees. The second question is, where can I find the report that will be issued tomorrow? That will be available on the NTSB website, which is at www.ntsb.gov. There will also be a press release that is sent out to all of the people that are registered with the website to receive those press releases, but it will be easy to find from the homepage. The next question that we have is concerning the article. So we developed a drop-in article, as Tom pointed out, that can be used by the associations. That information, that drop-in article, will be emailed to the associations along with the recommendation letter. And emails for all of the recommendation recipients will go out tomorrow morning at the same time that the report is available on the website. And also, just as a side note, the safety alert is also embedded in the report. So if you want a copy of that, the safety alert is available on the NTSB's website under all of the safety alerts, again, starting tomorrow morning. It is also part of the report as well. And so that ends the questions that we have here. Tom and I would like to thank you for attending the webinar today. If you have any feedback about the webinar itself, or about the information that we have presented to you today, please feel free to reach out to myself or Tom. I believe you have my email address from the information on the webinar. So again, thank you for your time and your attendance. This ends the webinar.